Hello Math 2412 students. I wanted to talk to you about the symmetries of the trig functions and a really good way of convincing yourself why the symmetries are the way they are, and also a quick way to memorize it. Okay, a little picture that will remind you. So if you put an angle theta and its opposite on the same unit circle, and here, in this side over here, I'm showing when p sub theta lands on to the right of the y-axis. Over here, I'll discuss what happens when p sub theta lands to the left of it. And that covers all the cases, right? But for example, here we have just theta is between 0 and pi over 2, so it's an acute angle, and there's its opposite. So you'll notice that p sub theta and p sub minus theta land on the same vertical line. So that forces, right, and that's by, you can make an argument by symmetry. If we reflect theta across the x-axis, reflect the triangle O, p theta, q theta across the x-axis, it's going to land right on top of O, p negative theta, q theta. And so the magnitude of the angle, the opposite of theta, so if you have a negative 30-degree angle, for example, that's how you put it in standard position. But the measure of that angle is, the magnitude of it is still 30 degrees. So p sub theta and p sub minus theta land on the same vertical line with equation x equal to some constant, right? But our definition of the coordinates of p sub theta and p sub minus theta, or whatever the x coordinates are, we're calling them the cosine of theta, the cosine of the opposite of theta, of that angle. That's our definition of the cosine. So they all have to be equal to that same constant. So therefore, the cosine of theta is equal to the cosine of the opposite of theta. What happens if they land those angles p sub theta and the opposite of theta terminate not in quadrant 1, right? So what if theta is not an acute angle? Well, let's say that theta is some angle that has several revolutions, but finally falls in either quadrant 2 or in quadrant 3, right? Regardless, its opposite curve, which is going to be symmetrically winding around but in the opposite direction, and is going to land, if p sub theta is in quadrant 3, p sub opposite of theta will be in quadrant 2, just by the symmetry of those angles being the same magnitude but in opposite direction. And therefore you can see, they're going to be on the same vertical line, x equal to some constant. So regardless of whether this is alpha and that's the opposite of alpha, or the terminating points, the cosine of alpha is going to be equal to the cosine of the opposite of alpha. So in any case, we're going to have the cosine of the opposite of an angle equals the cosine of the angle, and therefore the cosine is what we call an even function. That's the algebraic definition of an even function. You could think of y equal to f of x equal to x squared as another example of an even function, right? F of the opposite of x is equal to f of x. That's our definition algebraically of an even function. What happens with the sine? Back up to this picture. If theta is an acute angle between 0 and pi over 2, it lands in the first quadrant, and the opposite of theta lands in the fourth quadrant. By definition of sine as the y-coordinate of that point p sub theta, or the y-coordinate of that point p sub negative theta, we have, by the symmetry of these two triangles, by the similarity of these two triangles, O p theta q theta is similar to O p negative theta q theta, right? So the magnitudes of both angles are theta. So I'm drawing these as in geometry. I'm drawing these as angles. So that's a positive angle, and so is that. Right? They're just back to back. They're sharing the side OQ theta. So they have a similar angle, another similar angle, because those are two right angles, and they share a common side. Therefore, by the similarity of triangles, the distance from P theta to Q theta is going to be equal to the distance, or here I'm calling them the lengths, right? The length of the line segment P theta Q theta is equal to the length of the line segment P sub minus theta to Q theta. By similarity of arguments, you can get those two lengths, here they're written as lengths of those line segments, to be equal. All right, now P sub theta has coordinates cosine theta, sine theta. P sub minus theta has coordinates cosine opposite of theta, sine of the opposite of theta. When theta is between 0 and pi over 2, P sub theta is terminating in quadrant 4. And so its coordinates have to be positive and negative. So that value there is the opposite in SIGN. It's negative when this one, the y coordinate, is positive, sine of theta. Okay. So in the first quadrant, it's true that the sine of the opposite of theta, because it's a y coordinate in the fourth quadrant, has to be negative. Well, that's the opposite of the value of the sine of theta in the first quadrant. Okay, they're the same in magnitude. If you took the absolute value of one, you'd get the other, but they are opposite in sign. SIGN, right? All right, that's in the first quadrant. What happens if they terminate somewhere else? Whether they terminate in quadrants 1 and 4 or quadrants 2 and 3, you will see that the y coordinates will be opposite. Even if this is P sub minus alpha up here, and that will be P sub alpha down here, those y coordinates will be opposite in sign. So regardless of the size of the angle, theta, the sine of the opposite of theta is equal to the opposite of the sine of theta. That makes the sine function an odd function. Think of the cubic function, g of x equal to x cubed, right? If you plug in g of the opposite of x, that's going to be equal to the opposite of g of x. So that's the algebraic definition of an odd function. Okay, now, speaking of algebra, let's use a little bit more algebra. Let me get that glare off the lower half here. Okay, I think I accomplished that. There we go. All right, so now recall that using geometry, we had established these identities. Well, the book calls them identities. I call them definitions of those, for calculus students, of the tan, the secant, the cotangent, and the cosecant functions. Remember, they came out of the similarity of triangles OPQ, OSR, and UOT. We established this already using similarity of triangles. So, and we took and that was true for angles theta that were acute between 0 and pi over 2. Then we defined for any angle that these would be the definition of those functions. Okay, so now what happens when you stick in the opposite of theta, the opposite of theta, the opposite of theta, the opposite? Well, here's what happens. Any of those trig functions that involved a sign, you're going to see a negative sign coming through. The cosine, because it's even, kind of swallows that negative sign. But if there's a sine function in the ratio, then you'll see a negative sign coming out here. Now here for the cotangent, you'll notice that the cotangent and the tangent are reciprocal, right? You take 1 over the cotangent, you get the tangent. 1 over the tangent, you get the cotangent. So I'm just using that here. Since I just proved that the tangent here is an odd function, Then look at the cotangent of the opposite theta. Oh, that negative sign persists, and I have the cotangent is odd. The cosecant, because it's 1 over the sine, that's going to be odd. In fact, the only other even trig function is the secant, because that's 1 over the cosine. Okay.